Good morning, everyone. Welcome to the last bit of the lecture on gases. I can see just a few of us online. I hope the others are aware that our classes on Friday is at 8 a.m. Can you all hear me? Can you confirm I'm audible enough? Okay, you can hear me. Now, the last class we tried to solve some problems on Graham's law of diffusion. I think the last example we took, I got some feedback that there was a little error in the calculation. So I'll go back to that. I'll go back to that calculation. So we have the question, at a certain temperature, fluorine gas travels at 582 meters per second, and a noble gas travels at 394 meters per second. What is the noble gas? So, and in the usual way, we use the formula velocity of one of the gases divided by the velocity of gas 2 will be equal to the square root of the molar mass of gas 2 over that of gas 1. So in this case, our fluorine with atomic mass 19, and then fluorine gas will have molar mass of 38. So if we try to rearrange this equation to remove the square roots, we'll square the velocity of fluorine all over the unknown gas, so that the molar mass, their molar masses will not be in the square root sign. And so it means if we now make the molar mass of the unknown the subject of the formula, it will be molar mass of the fluorine gas multiplied by the velocity of fluorine divided by velocity of the unknown, all squared. So that's why we have that formula. Molar mass of the unknown gas will be molar mass of fluorine gas multiplied by the velocity of fluorine gas divided by velocity of the unknown gas, all squared. So I think it was at this stage that the other formula put it again in the square root. It's not supposed to be in the square root. So when we divide the molar mass, when we press our calculator, when we divide the velocity of fluorine 582 divided by 394 and you square that, whatever answer you get and you multiply by 38, you are going to get 82.9. If you look at the periodic table, that molecular mass is actually for 15 Kr. I hope the question is clear now. We can move on to the next example. So the next example, methane, CH4, moves 1.58 times faster than which noble gas? That's the next example we want to take. So, in our usual way, I paused because I wanted you to attempt this. The speed or the velocity of of the methane divided by the speed of the unknown will be equal to the molar mass of the unknown gas divided by the molar mass of the methane gas. So we are told that that of the methane is 1.58 faster than the unknown. So it means that methane will be 1.58 multiplied by that velocity of the unknown. That is the first thing we should take note of. Is 1.58 times faster. It means 1.58 multiplied by the value of that unknown is that of methane. So if we now put that into the equation, the velocity of methane now becomes 1.58 times velocity of the unknown. That's why we have it as the numerator. And then the denominator, velocity of the unknown, will now be equal to the molar mass of the unknown all over the square root of the molar mass of the unknown all over that of methane. Okay? So in the same vein, if we want to remove this square root sign, we are going to put a square on the velocity side. and so that the molar mass side will have it without the square root sign. So if we look at this velocity side, 1.58 v unknown all over v unknown, that v unknown will cancel out. And that is why eventually we have 1.58 all squared equal to the molar mass of the unknown all over molar mass of methane. So if we make the m unknown the subject of the formula, is going to be 1.58 all squared multiplied by the molar mass of methane. Molar mass of methane is 16. So if you multiply that by 1.58 all squared, then we'll get 39.9. And that, if we check our periodic table, is that of argon. So that noble gas is actually for argon. I hope it is clear. So in the absence of any question, we will move to the last bit of the lecture for the day. So we are going to be looking at the deviation. I want to reshare. Yes. So we have already stated the kinetic molecular theory at the beginning of the class, but we need to make some deductions, because actually the reality is that those postulates are for in an ideal situation. That is what we should have. But ideal situation is different from a real situation. When you say ideal, you say ideally, this is what it should be. But in reality, this is what it is. So ideally, those postulates are supposed to, be applicable for gases at all times. But in reality, it is actually, or it is not. It doesn't hold like that. So we now want to look at what are those parameters or conditions that makes gases deviate from ideal gas, or that will make real gases tend towards ideal gas. So of course, this we already know. Gases are tiny molecules, mostly in empty space. There are no attractive forces between them, and there are evidences actually to show this. Like the gases in tiny molecules that they are mostly in empty states. There is the evidence for that we can compress gas. There are no attractive forces between them. The evidence is that they do not cross. They move in constant random motion, in straight line. The evidence for that is that they mix rapidly. Okay, the molecules collide classically with container walls and with one another. The evidence for that is that the exact pressure that doesn't diminish over time. And then the average kinetic energy of the molecules is proportional to the Kelvin temperature. That is what Charles' law, the evidence is by Charles' law. Now, but there are deviations. What we have is that in real life, or the real gases deviate from the ideal gases. And this deviation is usually more pronounced at very high pressure and low temperature. If you look at the graph on the right-hand side, here you have PV over RT. When you put in those values at standard temperature and pressure, if you put pressure 1 atmosphere, volume 22.4, R 0.0824, and then temperature 273 Kelvin, and you press your calculator, you have 1. That is why at 1.0 is there. Under ideal gases, if you have that straight line, it should not change. That is what the graph is trying to tell us. It should just be on that line, parallel to the atmosphere axis. Okay. But when you now look at some of the real gases we have, if their graphs being plotted, you see we have that of nitrogen, we have that of CH4, we have that of hydrogen, and then we have that of CO2. You can see that all the graphs of these gases, when they were plotted, none of them followed the straight line like the ideal gas. Okay. When you look at very high pressure at 1000 degrees, 1000 atmosphere, at 800 atmosphere, and you trace to the graph, you see that they are more far away from that ideal line than when you look at about between 0 and 200 degrees Celsius. In fact, when you look at, I mean atmosphere, when you look at 200 atmosphere, you see that for a gas like nitrogen, you can see that it's almost close to that ideal line. Okay, and even generally, all of them seem to be more closer than at very high pressure. Okay, so at very high pressure, they are moving further and further away from the ideal line. It is at low pressure and at high temperature that the deviation is small. Okay, and I think the next graph we are going to look at. The next one we are going to look at is deviation from at high temperature. That's the temperature graph. If you look at for the ideal gas, still at our at 1 PV over RT equals 1, we still have that straight line. When we now look at a series of graphs plotted at different temperatures, look at the one at 200 Kelvin, the one at 500 Kelvin, and the one at 1000 Kelvin. You see that the one at 1000 Kelvin, very high temperature, is the one that seems closest to the ideal gas. As the temperature is decreasing, they are moving further and further away from the ideal situation. In fact, at a critical temperature, when the temperature is so low, the gas will be condensed to liquid. That is to show us that at very low temperature, those postulates that we say, oh, the gases, they don't interact, there's no molecular force. At low temperature, it doesn't apply. Otherwise, they will not have condensed to liquid. You know, in gases, in liquid, there is a force of attraction. So it means that when the gases are getting, when the temperature is getting really low, then there's going to be interaction between them. And that is why they can condense into liquid. So this behavior tells us that at very low temperature, ideal gas is no longer ideal. It is, the deviation is far from ideal. Okay? Now, in an ideal situation, that is the one shown on the left side, the A, molecules will travel in straight lines. But in a real gases, the path will curve due to the attraction between the molecules. Because when you look at it, when you have like maybe a stream or a river, and it continues to flow, when it flows and it gets to an obstruction, you will see the part of even the water we curve, we meander, in order to get past that and then now continue again. So that is actually what happens in reality. We don't just see them as just, you know, continue to move in straight line, just like that, as if the world is a straight path. No. So in reality, those gases, they meander, they assume some curves, and that is when the interactions between them is noticed. And a great scientist, J.D. van der Waals, corrected the ideal gas equation in a very simple but useful way. We shall see in a minute. What we should know is that there is no such thing as an ideal gas. Just like we say, in an ideal environment, we actually have an ideal environment. No. When we want to talk about our peculiarity here in Nigeria, so in an ideal situation, but the situation is not ideal. So it's the real situation that we are in. So the same thing applies to these gases. They are not, there's nothing like an ideal gas. But we can tend to behave towards an ideal situation if the conditions are right. Under ideal conditions. And from what we have observed in those graphs that we have studied, at high pressure, there's much deviation compared to low pressure. So it means at low pressure, the deviation is little. Similarly, when we look at the graphs under different temperatures, we'll see that at high temperature, they were more inclined towards the ideal situation. So the opposite, at low temperature, they are far from ideal. So real gases behave towards an ideal gas under two conditions: low pressure and high temperature. So still referring us back to that graph that we have seen, you know, I told you that PV over nRT how they got the 1 when you put in those values. The value of P at 1 atmosphere, V at 22.4, N equals to 1, R equals to 0.0821, and T equals to 273 Kelvin. You get 1. So this is just still trying to buttress or explain to us at low pressure at high temperature. That is when the gas behaves towards the ideal situation, like we have seen in the previous slide. So what did Van der Waals, what did he do? He developed an equation for real gases. And he won a Nobel Prize for this work. That is why we are sitting down here today, listening to the lecture, because of the great scientist Van der Waals. So if we look at what do we have for ideal and real gases, what is actually the situation with them? For the ideal gas, it is volumeless. That is what we were told. But actually, for the real gases, they have volume, a finite volume. For the ideal gas, we were told they do not interact with each other. But we have seen about a few slides ago that those gases actually, they don't travel exactly in straight line like that. There are curves, there are means of interacting with each other, making them take up space. Okay, so because they interact, they take up space, the volume of the gas is actually less than the volume of the container, like we assume for ideal gas. And the particles actually interact with each other. So what Van der Waals did was to bring up correction factors so that the PV equals to nRT, that is the ideal gas equation, he imputes some corrections into that equation. So we corrected for the volume of the gas, because according to the ideal gas equation, the volume of the gas do not have their own volume. They take up the volume of the container. But we have seen from the real situation now that those gases actually have volume. So he made a correction for that. And that correction is termed P minus NB. We don't need to worry ourselves where we got those values from. Those, yes, some of them are experimentally determined. So N is number of moles of gas particles. B is a constant. It's determined from experimental value, just like I mentioned. And then we needed to correct for pressure, because we have said that there's actually attractive forces between the particles. So meaning that the pressure that the ideal gas will exert is not equal to what is the real gas will exert, because the assumption from the ideal gas is that they do not have interaction. And of course, once there's interaction, it means it is going to reduce that pressure. You know, it's just like somebody going with so much energy and there's no body to collide with. You will continue to maintain that momentum. But as soon as he sees an obstruction, he's going to lose part of that. And so actually the pressure that we see in case of real gases is less as a result of attraction between the particles. So attractive forces will result in fewer collisions, resulting in less pressure. So we need to correct, as he needed to do the correction for the pressure as well.
Now, you're like 15 minutes, or I'll transfer it to my.
So the P observed is actually what is seen for the real gas, while the P the P with what's it called? These that are opening the in order to meet all the noise maker. So this is what we have. So the P observed and a correction factor. The P of the gas at the ideal gas minus a correction factor will give us the P observed. The P observed is that of the real gas. So that correction factor is also determined experimentally. And it depends on the concentration of the gas molecule, which means that the more the concentration of the gas, the more will be the interaction, which is normal. When you put when you crowd them, they will be able to interact better than when they are far apart. That's a function of concentration. So that correction factor is given by A n all over V squared. That is what Van der Waals discovered. A is a proportionality constant determined experimentally. Now, if we now put this into our gas equation, we have said the P observed is the P from the ideal gas minus correction factor. So our P ordinarily is nRT over V. Our P ordinarily is nRT over V. So it means that for the real equation, instead of saying nRT over V, it will be nRT V minus NV because we are correcting for the volume. And we put the correction factor for the pressure minus A n all over V squared. So we now rearrange this equation. Our P observed is equal to the P of the ideal gas minus correction factor. P of the ideal gas is nRT over V. V will also be corrected. Instead of V, it becomes V minus NB because we need to correct for the volume. And then we now subtract the correction factor Van der Waals gave us, A n all over V squared. When we now rearrange, we need to cross multiply. If we multiply both sides by V, if we take minus A n all over V squared to the other side, we will now get the P observed plus A n all over V squared. And then we now multiply both sides by V minus NB so that nRT alone will remain on this side. So when we multiply by V minus NB, the left-hand side will have the V minus NB, and then the right-hand side will only have nRT. So the first thing is take the correction factor minus A n all over V squared the other side to meet the P observed. And then that is why it is added here. So what is left on the right hand side will now be nRT over V minus NV. Then the next step is that we multiply both sides by V minus NV so that nRT is only left on the right side. So this is now what we have. This is our van der Waals equation. So P observed plus A into N plus V squared is what we call the P corrected. That is the correction for the pressure. Then V minus NV is what we have as the volume corrected. So the pressure corrected multiplied by the volume corrected equals to nRT. I hope we are following. Yes, somebody asked, the van der Waals equation, are we correcting for pressure and volume only? Yes, that's what van der Waals do, because that is what makes that ideal equation not valid, because the pressure is higher than what we will see for the real gas. And we have mentioned the reason being that there is interaction in real gas, so it will lower the pressure. And then the volume too is not the same as what the ideal gas equation states. And the reason is that we have observed that there is interaction, and then they will have their own volume compared to what the ideal gas told us, that the volume, they only occupy the volume of the container. So we need to correct for those two things. That is what van der Waals did. So we have the pressure correction, which is the A into bracket N over V squared. And then we have the volume correction, which is NV. I hope we are following. So that is our van der Waals equation. So just to reiterate, a real gas becomes like an ideal gas at low pressure. So, and why that is so is that at very low pressure, we have pressure and volume, they are inversely proportional according to Boyle's law. It means at low pressure, you have very large volume. So much large that the volume of the gas becomes insignificant because the gases are far apart. So real gas can tend towards an ideal situation if the pressure is very, very low, meaning that very large volume. Okay, so that is at one condition. And then it is observed, we said that B is experimentally determined. That B is smaller when gas particles are smaller. So when you have small gas particles, the value of B is small. When you have large particles, the value of B is larger. They are determined experimentally. That is what was observed from the experimental values. Also, another situation where the real gas tend towards ideal is at very high temperature. At high temperature, it means that the gas particles, they have very high kinetic energy and they can move randomly as much as they want at very high speed, meaning that there will be minimal interaction. And when there is minimal interaction, there is less chance of attraction. Okay, so that is when the P observed for the real gas now tend towards an ideal situation. So we have two conditions: at very low pressure, at very high temperature. So in summary, a real gas approaches the behavior of an ideal gas at very low pressure that is very large volume and at high temperature, when the gas experience little or no attractive forces. So what we observe is that the non-polar gases, they are more, the non-polar gases experience weaker attractive force than the polar gas. The polar gases have more tendency to behave real than the non-polar gas. So the non-polar gas have the tendency to behave more ideal than the polar gas, because in the polar gas there is attraction because of the polarity. So that brings us to the end of the class. If we have any question, you can ask. I'll try to see how I can send the notes across, but by and large, that is the end of this session on the world of gases. Do you have any question? So in the absence of any question, you can call it a day. So if you have a question, type it in the chat box. Let me see what question you have. Or you can, okay. Somebody asked, what are polar gases? Okay, let me give you an instance. If you have hydrogen fluoride, for instance, hydrogen fluoride, there is polarity between hydrogen and fluorine. Like in HCl, there's polarity between hydrogen and fluorine. Those behave like polar. But if you have something like H2, hydrogen gas, hydrogen, there's no polarity between the two hydrogens. So those are non-polar gases. I hope it is clear. So if there is electronegativity difference between the two atoms involved in the gases, then there's going to be a polarity, like hydrogen and fluorine, hydrogen and fluorine, ammonia gas, things like that. So, but when you have something like nitrogen gas, N2, there's no polarity because nitrogen is bonded to nitrogen. Like hydrogen gas, oxygen gas, there's no polarity because the two atoms that are bonded to form the gas, they are the same. But if the two atoms combining to form the gas, if there is electronegativity difference between them, there's going to be polarity. I hope that is clear. Yes, which one experience more attractive force between the polar and non-polar gases? The polar gas will experience attractive force because one is positively charged, one is negatively charged. So there's going to be an attraction. In the non-polar gas, there's no charge. So there's barely no attractive force. But in the polar gas, because one is positively charged and the other is negatively charged, there's a partial charge on them. So that is why there's more space or there's more room for interaction. So somebody was asking, what does A and B mean? They are constants and they are determined experimentally. I've mentioned that when we were doing the correction. Like in the case of B is a constant, it's determined experimentally. A is also a constant of proportionality. So we don't need to worry our heads about what the values are. If you need to do any calculation on them, perhaps in the nearest future, you'll be given those values for the gases in question because it differs from one gas to another. So a question is here, how do we know the value of R to use? It has different values. Yes, it has different units. So it is the pressure that determines what is the unit of pressure. If your unit of like R that is equal to 0.0821, that unit of R has the pressure in atmosphere. So if you are given calculation that has pressure in atmosphere, then you are going to use that value of R. If it is in Pascal, then you are going to use the 8.314. So it is the value of your pressure, the unit of the pressure you are given in the question that will determine the value of R you are going to use. If the value of, if the pressure is in atmosphere, then you are going to use that 0.0821. Because when you look at the unit attached to it, it is liter per atmosphere, blah, 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 blah. Then the other one, if they are giving your pressure in Pascal or kilopascal. I hope that is clear. What Van der Waals did was just to correct an ideal situation to make an ideal situation real. That is what he did by putting those values, those correction factors. So he was able to, those values or those that equation will not apply to a real situation. So what he did was just to correct, add correction factor so that real gas can also have their own equation. Do we still have any other question? Yes, somebody is putting up his hand. Somebody is putting up his hand. Do you have any question? So in the absence of any other question, we'll call it a day. And from next week, another set of lecturers will take over. So do enjoy the rest of the day and take care.